Yeah, I should, I guess, issue some kind of a warning that there are some people in the physics department here who are somewhat mathematically sophisticated, and that's not me. So I'm not trying to be humble. I'm just trying to acquaint you guys with the facts.
Well, remember, we don't know much physics. So.
Yeah, right. So, OK. So, yeah, I'm going to be discussing a quantum mechanics model that does seem to have some interesting connections to at least somewhat recent areas of mathematics, like from the 80s, some combinatorics questions, and Distermatt-Heckman formula, and hopefully a connection to random matrix theory. So, yeah, so it goes by the name of the Sachdev-Ye-Kitaev model, so SYK. And this is, it's an ensemble of sparse random matrices. And when we think about elements of that ensemble as the Hamiltonian for a quantum mechanics system, then it defines a quantum mechanics system that shares some properties with a very simple black hole, a black hole in a two-dimensional space-time, so a black hole in a theory with one time direction and one space direction. So that's an interesting property of these Hamiltonians. But OK, so the black hole information problem, which is a big problem in my area in physics, leads us to consider quantities in this theory, in this quantum mechanics system, that are connected to quantities that people often study in the context of random matrix theory. And we would like to be able to calculate those quantities, ideally for black holes, but less ambitiously, we would like to be able to calculate those for this particular ensemble of sparse random matrices. So that's what I'll discuss. So I hope that you guys will interrupt me whenever you like. I have stuff to say, but I'm not. Yeah.
It's supposed to be very informal.
Yeah, I'm not. I don't have an hour of material prepared, and I'm not committed to getting to the end of it anyhow. So I hope that you guys will interrupt me. So. OK.
Is there any other connection between black holes and random matrices?
Well, so the basic connection is that a black hole should be thought about as a quantum mechanics system, where the time evolution is some matrix, some Hamiltonian.
Is something supposed to be chaotic?
Yeah, and it should be. Black holes are strongly chaotic systems. So we could discuss how we know that and how we can compute that, but they should be strongly chaotic quantum mechanical systems. So they should be described by Hamiltonians. The time evolution should be given by a matrix, which has at least some well.
So is the connection the usual one between sort of quantizing a classically chaotic Hamiltonian, then the Hamiltonian, the operators should look like GOE or something.
Yeah. This, I guess, is probably somehow a different limit in the landscape of quantum chaotic systems, where the black hole would not be a system. It's not
a high frequency.
Yeah, it's not a classical system that you've quantized. It's not a classically chaotic system that you've quantized. It's sort of, from the get-go, a quantum mechanical system. But it's expected that shares, that this also enjoys this random matrix universality that has been understood to some extent in these.
The explicit connection, is that new? I mean, that's my big impression.
Yeah, it's new that one is trying to take it seriously, and that what's new is that we have a quantum mechanics system which is related to black holes, and where we can actually compute the spectrum, the exact spectrum.
Okay, so
That's I'll tell you what it is. Okay, so it's a quantum mechanics of n Majorana fermions. So Majorana fermions are, for our purposes, they're matrices, psi I, where I runs from 1 up to n, so there's n of them. And they satisfy the following algebra, that psi I times psi j plus psi j times psi I is equal to 2 times delta ij. So we say that these things anti-commute if I is not equal to j, and they square to a multiple of the identity if I is equal to j. OK. Now these things, the only important property of these is this relation. And you can realize you can realize this algebra in a space of dimension L, where L is 2 to the n over 2. So this is the dimension of the Hilbert space. Okay?
You're now realizing as matrices.
Yeah, so now we think of these, we should think from now on, we think of these psi i's as completely explicit matrices, which are L by L matrices living in this space. So the simplest example would be if we have n equals 2. Yeah, I should mention that n is even. We have to have an even number of these fermions. So the first non-trivial case is n equals 2. And then we could take, as the matrices, we could take psi 1 is 1, 0, 0, minus 1. And psi 2 is 0, 1, 1, 0. And you can check that this holds. Yeah, we should put, yeah, this holds for these matrices. OK, but for larger values of n, there's a procedure for generating these matrices. And the minimum size would be 2 to the n over 2, and we'll assume that representation. OK. So that's what Majorana fermions are in quantum mechanics. Now the Hamiltonian is the following. So we build a matrix as a sum over all possible products of 4 of these fermion operators. And we sum over all possible products with a set of coefficients j. And these coefficients j define the ensemble. So we take these things to be random and Gaussian distributed with a mean that's 0. So j with indices here is 0, and j squared. So j squared. So the variance of an individual one of these guys would be given by parameter j squared. It's convenient to put in a particular normalization. These factors aren't too essential. The important point is that the mean is 0, and there's some variance for these coefficients. Okay.
So this j square means just the square of each coefficient.
Yeah, that's right. Yeah, it's important that here I'm not summing over indices. Let's say
They're independent guys.
they're independent. Yeah, they're independent. Thank you. Yeah, is this completely clear? Maybe.
Maybe everybody should say something if it's not here. But
Yeah. If you want, so for example, suppose I want to generate these matrices on the computer. I'll form an explicit representation for these guys. Then I'll sum over all products of 4 of them. And then I'll ask the computer to generate for me a random Gaussian number with this variance. And I'll multiply it by that. And then I'll move on to the next term. And I'll keep doing that. OK, so we'll do that roughly n to the 4th times. Yeah.
So I heard someone say, maybe I misheard, that this is a vector model. Like, how is this a vector model?
Vector model? Yeah, it's a vector model in the sense that the variables that we consider have one index. So they have one, so they're labeled by one index I,
So the vector
psi
is
I.
the-
Yeah. Often in physics, people consider, well, they consider degrees of freedom that have 2 indices. Those are often the more interesting theories. Vector models are often very, very simple, but this one is interesting, even though it's sort of like a vector model. There's a generalization of this that is often useful to consider, where we replace 4 by q, and we have a Hamiltonian involving all possible products of q of the fermions. So these should be thought of as Hamiltonians where we have these Majorana fermions that are interacting in groups of q. So
Is the sparsity this 4? What you said something is going to be sparse.
yeah, the sparsity.
That you have this only 4 interaction.
Yeah, that's right. That's right. So these matrices here, these psi matrices themselves are sparse. They have roughly as many entries as just like a diagonal matrix. And we're not summing over very many values. We're only summing over n to the 4th or n to the q values. So yeah, it's very important to keep in mind these 2 parameters here.
And L is much larger.
L and n. So yeah, it'll be important that the size of the matrices we consider are L by L matrices. So the Hamiltonian is an L by L matrix. And we
I guess
consider.
in quantum computation, these are the kind of gates that you could. Did Kitaev develop this for the purpose of quantum computing? Or?
No, he actually developed this for the purposes of thinking about black holes. So, yeah.
By the way, he told me that at the end you will explain a problem to us.
A problem.
Yeah.
Yeah, well,
There are many of them.
okay.
That's what he
Yeah.
told me last week.
Okay. Okay, well, we can see, yeah. Okay. Good.
So these are mean field models. I mean, they have no spatial structure.
That's right. There's no space.
And I mean, is there anything like replica symmetry breaking or that kind of thing that occurs here as it does in
Yeah.
spin glasses?
Yeah, this is an interesting question. So in the past, people have written down Hamiltonians that look structurally similar to this.
Yeah.
Often they write them down not in terms of Majorana fermions, but in terms of Pauli spin variables.
Yes.
And those things are known to be, at low temperature, to have spin glass behavior. And this model is different. So
Why
at
is it so different? I mean, because it looks quite similar, right?
yeah, there are different ways of explaining why it's different. I'm not an expert in spin glass physics, so I can tell you the arguments that people who know about this offer.
And yeah, there won't be
But-
any
No,
replica
no.
symmetry breaking.
No, and actually one can check for that by just so you can assume there's no replica symmetry breaking and compute things like the free energy and compare those to exact numerical computations, and you find excellent agreement, which you would not have found for these spin glass models. So
When you say numerics, you can't make L very large.
no, so we'll get to that.
So,
Yeah, so numerics.
If you see anything, you make
Well, you can get L to 150,000 or something, and yeah. So that's the largest.
make L large, sorry, I mean you can't make N large.
Yeah, n is at most 34. And okay, so yeah, so just to be completely clear, what we mean by this Hamiltonian in the quantum mechanics system is we think about this matrix as the Hamiltonian, and so we would evolve states with the Schrödinger equation. So this would be a vector now that lives in the L-dimensional space, and we have this equation. Okay, so that's what we do with these matrices when we think about them in the context of quantum mechanics. So we can discuss in more detail. I'm not sure which aspects of this will interest you guys, but we can discuss in more detail to what extent this system is similar to a two-dimensional black hole. But maybe,
H is supposed to be self-adjoint,
yeah, yes, that's right. H is Hermitian.
so you make some assumptions on, is it clear whether
J's are real?
The J's just have to be real. Yeah, actually, I should
And
have.
the things are probably unitary.
I should write here a factor which is q over 2 here. And if we do that, then the Hamiltonian is always Hermitian. These sides themselves are Hermitian, but they anti-commute, so we have to check. And depending on how many of them there are, they might or might not develop a minus sign. And so this I accounts for that. Yeah, that's right. The Hamiltonian is Hermitian. OK, but this model is supposed to be an example of a sort of a toy model for ADS-CFT, where we relate quantum mechanical systems to quantum gravity systems. So this is a quantum mechanical system living in a theory of 0 space and 1 time, and it's related to a quantum gravity problem in 1 space and 1 time. So that's the way that these.
By quantum mechanical system, you just mean e to the I th.
Yes, yeah, but it's a system.
Algebra, it's nothing else.
Yeah, it's a system without any spatial locality. So yeah.
Everything's linear algebra.
And setting up the linear algebra is what these guys are good at.
Oh yeah, no, that's. As I said, I'm not one of the mathematically sophisticated people, so linear algebra is enough for me.
I guess if Q gets large, and you average that, that would go to, I'm sure very easy to prove, goes to one of your standard Gaussian ensemble.
Yeah, so actually I would be interested to discuss this more. So you could write exactly GUE or GOE as a sum over different values of Q. And now,
I'm sure that if you average in any way over Q, you get either GOE or GE or GSE if you put in extra.
for large values of large but fixed values of Q. Okay. Yeah, I think probably when Q is of order n, there are.
I'm only saying Q goes to infinity n fixed, then it's obvious, but otherwise.
Well, Q can never be bigger than n, because we have at most n fermions.
So it's a bit subtle.
You can write the exact GUE ensemble as a sum over this thing with different values of Q. But that, well, okay, that's one fact. Okay, so now we could discuss the types of things that we compute in this model. So one example of a thing.
Wait, you were going to tell us one word what it has to do with black hole?
Yeah, I can do that. So yeah, maybe I can say that. I can say that in words, and we'll see a little bit an equation later. But this model can be analyzed. This model can be solved at large n in the 1 over n expansion. And the way that one does that is one integrates over these couplings j, and one does the disorder average over j. And then you get a rather complicated theory, but it's a complicated theory which has this large parameter n that allows you to solve it in an expansion in 1 over n.
Is it a saddle point or
Yeah,
a
that's
saddle manifold? Or
yes, that's right. That's right. And so you can think about this. This becomes now now an integral with a saddle point parameter which is n, and we study the 1 over n expansion. And you can show that correlation functions of this model in the 1 over n expansion agree with correlation functions that you would get in this theory of the two-dimensional black hole. One of the most interesting types of
In quantum, I understand what you're computing. What correlations are you computing with black hole?
yeah, so that we would consider a black hole spacetime, and we would compute correlation functions of fields propagating on that space. So
And is this something of local correlations?
these would be correlations of operators at different times.
the
So
only
as a
time-
function of the time.
Yeah, there's no
It's
space.
only one space.
No-
And
no
here,
space.
well, the two-dimensional problem has space.
But
but
there's no space here, really.
There's no space here, so what we compute here are quantities that depend only on time, and those would be quantities in the two-dimensional problem that are at the boundary of the space at different values of time. And so you can compute,
That's the holography.
yeah.
That's the-
So you can compute those things for this black hole space-time using gravitational perturbation theory and compare that to the 1 over n expansion of this theory. And well, the thing that's been computed in detail is the 1 over n term, and this agrees in a precise way. We can make this more precise later. There's, of course, much more to say about this. This is the main thing that has been studied about this model. But that's,
Coupling will be 1 over n times k squared.
sorry?
The coupling will become 1 over n times j squared.
Which coupling?
The large n.
No, good. So I should clarify this. The regime where this model is related to a black hole is actually at large j, where this parameter is large. So we take this parameter to be large, or equivalently, we can just study the model at low temperature, and then we do the 1 over n expansion. And so the 1 over n expansion at large values of j is the thing that agrees with this two-dimensional theory. Yeah. Okay. So yeah, we could discuss these correlation functions that we compute, but maybe a simpler thing to discuss is just the partition function. So we can consider this quantity, which would be a sum over all of the energy eigenstates. So that's a sum that runs from 1 to L, e to the minus beta times Em. So Em is an energy, a eigenvalue of this matrix, of the Hamiltonian. And we consider this type of expression. Now, it's a general feature of this type of sum. Yeah, let's think about this type of sum for a second. If t is small, let's say t is 0, then we're summing up a whole bunch of positive quantities. But as we increase t, then these phases here cause some partial cancellations in the sum. And this function will decrease as a function of time. So it starts out large, we're summing a bunch of positive quantities, then we're adding phases, and it starts to decrease. But it doesn't decrease to 0. Sums of this type are, I guess these are things that are called like almost periodic functions. So it will become rather small, but it will oscillate, and at very long times it will have recurrences back up to its initial large value. So that's the behavior one expects for this type of function, this type of partition function. Now, you could also try computing this type of quantity in gravity, in the two-dimensional gravity theory. And there, in the perturbative expansion in the gravity theory, you find that this type of expression should actually go to 0 at late time. So we know that in any quantum mechanical theory where we can write this as a sum over energy eigenstates, this should not go to 0. It should oscillate at late times. But in a gravitational computation, you find that it does go to 0. And this is a symptom of, this is maybe the simplest symptom of this thing called the black hole information problem. So understanding how these gravitational computations are misleading is a huge problem in theoretical physics. People don't have a lot of good ideas.
Because that's a classical calculation, or it doesn't include the quantum.
It does. You would include the quantum effects in gravity theory perturbatively. So you imagine that you have a small parameter that suppresses quantum effects, and you could imagine computing this thing in a power series in that parameter. And to any finite order in that parameter, you expect to find decay at late times.
But quantum mechanically, you do not.
Yeah, that's right. So you know that the actual answer does not do that, and you don't know how. Yeah.
Well, so the fact that quantum mechanics, you say that it oscillates, I think it's a consequence of finite dimensionality. Infinite dimensions, you can have continuous spectrum in which it actually does decay.
Yeah, it's not. You're basically right. It's not even so much that the dimension is finite or infinite. It's that the entropy, the spectrum has no accumulation points. Yeah. Well, no. The spectrum can be infinite. The spectrum can be the Hilbert space can be infinite, and you still have this quasi-periodic behavior. The important thing is that the entropy should be finite. The spectrum not have accumulation points.
Not exactly.
No.
That's math, don't worry.
Okay. I mean, it's very common in quantum mechanics to have systems that will have almost periodic partition functions, but have infinite dimensional Hilbert spaces. We could take like yeah. Okay. 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 I'm sure. Okay. I don't know. Okay. So so the thing we would like to do is understand this function in the SYK model and see if we can understand how this 1 over n expansion.
The condition is just simply the Fourier transform of the measure, of the spectral measure, and that's why it's just given in terms of the absolutely continuous part with decay. Point spectral part will have a feature you're talking about. There could be some weird stuff that you don't want to hear about.
Okay. Yeah.
Just so I'm clear, so from the physics point of view, what is the problem?
Yeah, from the physics point of view, the problem is that black holes appear to, the way that we know how to compute things in black hole spacetimes gives us expressions for this type of quantity that would go to 0 at large time. But we believe that quantum mechanics, that black holes are finite entropy quantum systems. And for finite entropy quantum systems, this should not go to 0 at late time. It should be an almost periodic function, and it should have this oscillating behavior. Now,
you're going to see features of that in this
yeah. Now, of course, here we have an honest quantum mechanical system, and it will not decay. So, on the other hand, it shares some properties with black holes. So, hopefully, we can use this to understand better how to. Yeah.
Quantities like that, could you give a physical meaning to such quantities like that?
Yeah. So this, well, the quantity that one is normally interested in is not this partition function quantity, but a 2-point correlation function. Let's say of 2 of these fermions at time 0 and time t. And then we would take the time t to be very large. And we would have the same situation, where the gravity theory would predict that the 2-point function should decay at large time. And the quantum mechanics, the finite Hilbert space computation would show that it would not decay. This one also has a physical meaning, but it's sort of a funny, it's an analytic continuation of a partition function. It's not as clear as the 2-point function, but it's simpler to write, to compute. Okay, good. So we could imagine computing this in the SYK model. And more precisely, we could imagine computing this in the disorder average. So we would compute z as a function of these couplings j, and then we would average them over j. Now there's a problem, which is that if we average this spectrum, we have a continuous spectrum. And indeed, this function can decay to 0, and it does. So the disorder average of the partition function decays to 0 at later time. But for a given realization of the model, the typical value will not be 0. What that means is that we can consider a different quantity, which would just be z times the complex conjugate of z. And then we can take the disorder average of that quantity. And now cancellations are not possible from the average over j. And this is something now that really should not go to 0. So let me plot. Yeah, okay. Should I continue writing on these boards? Is that better? Maybe I should just do that.
All the boards are.
Maybe I'll just do that. Okay. So now the thing is, we just numerically diagonalize this Hamiltonian, and we study this for many different values of j, and we plot the answers. So we define a function g of t, which is the average over couplings.
You numerically generate a random j.
Yep. So the numerical procedure is generate these random couplings j, diagonalize the Hamiltonian, compute this thing, and then move on and do it again, and do it many times until we get a nice smooth function. So that defines g of t. And here's what it looks like. So I'll plot it as a function of log t, and here's log g. So this is a log-log plot, and it looks something like this. Okay. So good. So this is for the largest values that we can study numerically. Our n is equal to 34, and L is equal to 2 to the 17, which is like, I don't know, it's like 150,000 or something like that. So let me draw some rough indicators of the scales of the different places on this plot. So the initial value here is when we have no phases entering in the sum. This expression here would have been of order L, because we're adding up L things with no phases. We're squaring it here to define G. So this thing is of order L squared. So G. Yeah, beta is fixed. We could imagine maybe the simplest thing for the moment. To get exactly this shape of plot, you would take something like beta times j is about 5 or something, some order 1 quantity like that. We could study these functions when beta is 0, but let's not do that.
Why 34?
Well, that's just the largest number that we can.
32, I would say, yeah, fine. But why 34?
Well,
They have to diagonalize the matrix again.
no. So 32 is you have to diagonalize a matrix, which is 2 to the n over 2 by 2 to the n over 2.
Why not a power of 2?
Why would a power of 2 help?
Well, because that's, I mean, it fits in with the limits of what you can fit in memory.
No. The n being a power of 2 doesn't help you. We're studying e to the 2 to the n over 2.
Mm-hmm.
So that is a power of 2. That's 2 to the 17.
The big N is 30.
Yeah, this is the most important thing in the talk. I should emphasize again. N is the number of fermions. We should think of this in these things as being n equals 34. L is the dimension of the matrices that we're studying, dimension of the Hilbert space. This is 2 to the n over 2. The fact that these things are very different from each other will be very important. This is really the central aspect of this.
So L is 16 bits. You can encode L on 17 bits. Sorry. Okay, it's fine.
Yeah, yeah.
I'm just a little surprised.
I mean, for these values of n, the limiting factor is time. It's CPU time anyhow. So yeah. I should have mentioned before I started that there's a long list of collaborators I have that are working on this, and I'm not doing this matrix diagonalization, and so I know some small amount about that, but that work is being done by many by other people. So I can list the people, but you guys probably don't know them, so maybe you don't care.
Yeah, you collaborate with one.
Yeah, but he's not part of this project here. But yes.
We're just recording this to show it to them.
Okay, good. So my esteemed collaborators, yeah, I'm not going to list them. Well, I will if you want, but okay.
We don't care, we don't know them.
Yeah, that was my thinking. Okay, okay. So the initial value is g is of order L squared, so that's big. The final value here, well, and we'll explain where this comes from. G is of order L. The time where this transition happens is a time that's of order L, and the time that happens here is a time that we don't know very well. So that's.
And when you say this, you run it with different J's, and it's always the same picture.
Ah, great. Yeah, thank you. I should have clarified. Let me plot now on top of this a typical run with one value of j. So instead of averaging over the j's, just a typical thing. That would look very similar here. And then after this point, it would do something like this. So the function here is the technical term is that it's self-averaging before this time, and it's not self-averaging after that time. So given realizations look different from the average.
Looks like a regularization of a shock, right?
There's a concentration of measure onto that.
Yeah. So we can understand why this is self-averaging at this point and not later as well.
And this amplitude of the oscillations doesn't decay.
Yeah, no, the oscillations are always of order the function itself. So yeah.
I mean, in the end, if you take t large enough, you're just getting the guys which are coefficients
Yeah.
0.
Yeah, I mean, it makes sense. Yeah, that's right. But it makes sense that this z.
Function it means.
Yeah, the z's were very large values of time, or a sum of a whole bunch of sort of random things. So z is Gaussian distributed at large time, and that's why these fluctuations are of order the size of this thing itself. Okay.
What kind of thing is why does that thing happen when t is of order?
Yeah, I will explain that. I will explain that. But I'd like to draw a. Okay. So the moral labels that I would like to attach to this are the following. Here's some time here, which marks the transition between the part I'll call the gravity part, or more precisely, the 1 over n expansion part, where we can understand this curve by thinking about the 1 over n expansion. And then this part, I'll label the random matrix theory part. And for this thing, we should think about a 1 over L expansion. Yeah. OK, so I'll explain why we're thinking about these two different expansions. So first, we'll discuss this gravity part. In this region, because this expression is self-averaging, rather than thinking about the average of the square, we could just think about the average of z.
The L might guess if that matrix is connected to Dyson spectral rigidity. You know that? Say 1 over L.
Yeah, the behavior.
The fact that it's only log of n, that's a feature of the variance of the eigenvalues in random matrix theory.
The fact that it's 1 over L is, yes.
The variance is tiny.
Yes. But explaining how you get that small parameter from starting from 1 over n expansion is.
Not in your model. Ordinary random matrix.
Yeah. Good. Well, okay, good. I want to get to that. That's the main thing I would like to discuss. But let me first comment on the gravity part. So this is the part that we can understand. This part we haven't really understood how to think about this correctly, directly in the model. This part we can understand from the model itself. And there's a right. So we would be thinking about the disorder average of the partition function instead of the square in that region. And basically, we can just do the conventional thing for this type of model, which is the 1 over n expansion. And so what one finds, there's a long analysis that one has to go through to compute the effective theory of these fermions at large n and at low temperatures. And it has actually, I just want to write this formula because it has a beautiful, it's quite beautiful. But this becomes an integral over this symplectic manifold diff S1 mod SL2R of whatever the volume form, and then a particular action, which is n over beta j, where beta is now, I should write beta plus it, times the integral of the Schwarzian derivative of some field phi tau, where the Schwarzian is phi triple prime over phi prime minus 3/2 phi double prime over phi prime squared. And phi here is a element of diff S1 mod SL2R.
So the measure on this big infinite dimensional space, this is some functional integral.
Yeah.
Can you reduce it? I mean, that's something that
Yeah, this integral is a it has a remarkable fact that this functional integral can be computed exactly using this Duster-Heckman theorem. So this is an integral over symplectic manifold of the exponential of an exponential of a generator of a U1 symplectomorphism of that manifold. And so the integrals of those things are easy to compute. And so the answer for this functional integral is equal to exponential of n over, I should write, beta plus it j over the same quantity Okay. So this has a very simple answer.
Sorry, I don't completely understand notation. What's n small?
Sorry?
What's n small in the first factor in the...
Where's n? Oh, this is the dimension of the space. So what I really mean here is the symplectic measure on this space, diff S1 mod SL2R.
Okay. Oh, I see.
Yeah, it's an infinite dimensional space, so that little n would be infinity.
So this is an equality.
Yeah, this is
an equality by Duster-Heckman. So
yes.
You can reduce it to the critical manifold.
That's right.
Of this action.
Yeah.
And then divided by. Then you have to look at the Hessian.
You have to look at the one loop term. Yeah, that's right. The Hessian about that point.
You can see that the integrand is SL-GAR invariant because of the Schwartzian.
Yeah.
By dividing by it. But
Yeah.
Where did the Schwartzian come? That comes from the calculation.
Yeah, that comes from the calculation. And this part I don't have time to explain, but this is actually a long calculation that starts from these fermions, and then in the low temperature limit of that model, you get this effective theory, and that's not at all obvious. And
So who did this calculation first?
so this
Is this Sachdev or not?
no, this was suggested in talks by Kitaev, but it was worked out in detail in the paper that I wrote with Madasena. But
And there were some corrections to this that he talked about.
Yeah. So but those things are not important at low temperature. So we can discuss the other reason that I wanted to write this formula here is that this theory here is exactly the theory of this two-dimensional black hole. That's also something that's not completely obvious, but this is how that link is made. You study this problem at large n and at low temperature. You have this effective description, this computation of the partition function, and this is exactly the theory of the two-dimensional black hole. So that establishes the link between this system of fermions and the black hole. This is the entire two-dimensional dilaton gravity theory is exactly this integral. So that has a simple answer as well.
And the quantity on the left for the black hole
would be the partition function in the effective theory. It would be the same thing.
Boundary, right?
Yeah.
Time.
Well, the partition function for the space-time of the black hole. You don't have to. Yeah.
So for another question, so what does S1 correspond to in the theory of black hole? Does it mean the space is compactified or what?
Yeah. So we're thinking about this. The black hole it's a theory in we should think about the black hole in Euclidean signature space. So the finite temperature is related to the periodicity of time in units of the inverse temperature, beta. So the time is compactified, and the two-dimensional theory reduces to just an integral over these diff S1 mod SL2R. By the way, if anybody here is an expert on this space, I would be interested to discuss.
The expert is actually Kirillov at UPenn.
Okay.
We can bring him up.
Okay. Yeah, I would love to. I think there's more. I believe there's more somewhat subtle mathematics lurking in this thing here that I have not understood. There's one very beautiful thing, which is that you can exactly evaluate the integral, but there are other things that probably can be evaluated exactly that I don't know how to evaluate.
I mean, this is a bit like this old string theory becoming integrals over modular space with this kind of Polyakov formula, which became the infinite dimensional integral of the action. And then you apply your formal manipulations and get it down to some finite integral which you can only compute.
Yeah.
It's that kind of. See, we have
I have
a problem with
functional integrals. Yeah. Yes, I understand there's this cultural divide, but well, this one nobody has a problem with. So, okay. So anyhow, the one point is that the partition function here at large values of t is going like 1 over t to the 3/2. Now we take this expression and square it, and we get 1 over t cubed, and that explains this part of the curve. So that the part of the curve to the left of this point here is explained accurately by this formula. So now we can proceed. Now we've understood the part of this that we can also compute in gravity, and we see that it agrees with the numerics. So now we can proceed to try to understand the rest of it. And that, well, we have some ideas for this, but we don't have much direct understanding in terms of the original model. So what I'm going to do instead is describe the computation of this same quantity in random matrix theory, in particular in GUE. So let me just, well, I don't have to draw the same figure again, but I can just tell you that if you compute this where we replace the Hamiltonian with a random matrix, an L by L random matrix, then the curve looks, to the precision of my drawing, exactly the same. So now we can
random matrix, you know,
Which
2 to the 17 by 2 to the 17 or something.
Yeah, that's right. So actually the ensemble depends on the value of n. It's periodic in n mod 8.
Is it actually a random 2 to the 17 by 2 to the 17?
Yeah.
Because it seems like the original Hamiltonian is very sparse.
Yes, but let's consider a different problem, which is a random matrix, and just plot it.
It still gives
And it gives something that looks very similar to this. Now,
Sally would suggest that they would be the same anyway.
those should be the same at late times. So now let's discuss where this. So we need to understand what part of the random matrix theory this curve comes from. In particular, we'll be interested in this part of the curve from this point onward, since we already know how to explain this. Okay.
I'm confused. With the random matrix theory, you reproduce the whole curve or just the right side of the curve?
You get a different curve, which disagrees with the curve to the left of here and agrees quite well to the right.
But it's different on the left.
It's different on the left. It's not as different as you might think. The reason it's not as different as you might think, in particular, it has the same slope, 1 over t to the 3/2. The reason for that is that the random matrix, this could be described just by the partition function, just by the mean density of eigenvalues, which vanishes like a square root for the random matrix. Now, vanishing like a square root, if you plug that in and compute z, translates to this power 1 over beta to the 3/2. So it's the square root vanishing of the density of states that gives you these things. You could ask then, what is the density of states that would give you this function instead? I can just write that. That would be the density of states rho of E is like sinh of square root NE over J. So it vanishes like a square root at E equals 0, but it's not the semicircle. So that would be the behavior for small energies in this model. And that the fact that it's not exactly the semicircle tells you that it's somewhat different from, this part of the curve will be somewhat different than what you get in random matrix theory.
What would say the road of J in the GUE?
Yeah, that would be the width of the semicircle. So that's just the overall scale of the matrix.
And you said something about whether this is GUE or
right.
or
Mod
GOE or
Yeah.
something else or
This
GSE or
This depends on n mod 8.
And then only just amongst two of them, GOE and GUE, or the tenfold way? What?
Half the time it's GUE, the other half is evenly split between GOE and GSE.
Oh, okay, so just the three.
Yeah.
standard.
Yeah.
There are none of these exotic ones that come from the tenfold way or
No, and actually I don't understand those. So
So we can talk about
okay.
an expert.
Yeah. Okay. Good. So let's think about how we would compute ZZ star in GUE. So we would write this as an integral over a pair of eigenvalues, lambda 1 and lambda 2. And then we would put here the GUE average of this pair correlation function. And then we would have, let me set beta equals 0. Then we have e to the I times t, lambda 1 minus lambda 2. OK, so we would be looking at basically a Fourier transform of this pair correlation function. That would be giving us this z. And for GUE, the answer for this expression here is L squared. So the density of eigenvalues is large. It's proportional to L. We have 2 copies of these, so we get an L squared. Now we would have rho naught of lambda 1, rho naught of lambda 2. These are just the semicircle mean density. And then we would have 1 minus the sine kernel expression. Where here lambda, you're right, lambda would be a rescaled version of lambda 1 minus lambda 2. It's this thing over something like this. And we would also have a delta function piece with a coefficient L. OK, so this is a formula from random matrix theory. And we can just evaluate this Fourier transform now. The part of it where the large part of it, large L, comes from this 1 here. And there we would just take the product of the Fourier transforms of the two semicircles. And that would give you the thing I described. That actually gives a Bessel function. If we square the Bessel function, we get something that decays like 1 over t cubed. It looks rather similar to the first part of the curve, but it's not exactly the same because the mean spectrum is different. So now we have to understand the rest of it. So this Fourier transform can be computed exactly. It gives actually this tent function that is linear, and then 0. And then the contribution of L gives just something that's constant. So these two terms together give a function that does this, that is linear in time. Maybe I should draw it here.
Usually called the form factor.
Right. So this expression is what's known as the spectral form factor in the quantum chaos and random matrix theory literature. And so this answer, we would have something which was, I think it's J1 of t over t squared in this region. And then we would have something which was, it would intersect this. This looks like t over L. That's the Fourier transform of this guy. And then at a time of order L, it would become constant at a value of L. Sorry, this is just t. I apologize. The value of this thing is just t. The value here is L. This corner here is at a time of order L. So this is the answer for this curve in GUE. You could ask about it in GOE or GSE. And there what happens is that this linear behavior is modified a little bit in this region here. You would have a whole power series of 1 over L corrections. An important feature of this computation is that it's, in the random matrix theory variables, it's a perturbative computation in 1 over L. So for example, in GOE, you have a whole power series here in powers of 1 over L. So for this reason, this part of the curve is labeled 1 over L. You're supposed to think about this in 1 over L perturbation theory instead of 1 over N perturbation theory. And these are very different. So this is the thing that we have not understood. Well, OK.
So of course you understand the random matrix theory because you computed it.
That's right.
And so what is missing? Of course, so you don't know why the two are the same. I mean, is that just part of the question?
We don't know that, but yeah. So the overall thing that motivates us, at least that motivates me, is to try to understand for the black hole why these functions don't go to 0. OK. And so for that, it's the only tool we have for thinking about black holes is the 1 over n expansion, where n is the big parameter. And we can think about other types of corrections as a function of n. Here, we would like to understand in this model, where we also have this 1 over n parameter, we would like to understand somehow how that expansion becomes bad, or how in this model you eventually have to think about a 1 over L expansion.
Well,
so
I can just make one very brief comment, which
yeah.
is in the old days when people did random Schrodinger perturbation theory, they could not see these oscillations, which of course you can see with random matrix theory, because you have orthogonal polynomials that will.
You mean oscillations in the row of E?
These kind of sign.
Yeah.
If I take a random Schrodinger operator, one does perturbation theory in coupling constant, for example, then you see a lot of what you're talking about, but you cannot see these oscillations. However, if you go to an integral representation, which is there are many ways to see it, but if you write it supersymmetrically, then these are the contributions in the zero modes, which are invisible perturbatively.
Okay, you're thinking about the oscillating term as a function of L. Yeah, this is this Andreev Altshuler instanton.
Yes.
That's you're right, right,
Related,
right,
yeah.
right. Yeah, that's right. So that's good. So we have 1 over L. You have so to describe this ramp, this region here, you would do 1 over L perturbation theory. But to describe this corner region in detail, you would want to do e to the minus L. You would have to include e to the minus L corrections. So this is another level of exponentiation that we don't understand how to get, starting from the theory where n is the big parameter. So this is the type of challenge, is to try to compute this curve.
I mean, for example, would you say that if I looked at that Hamiltonian and I looked at the level spacing in the bulk,
Yeah.
then I would see GUE or GSE? Or
You're talking about, for example, the nearest
The-
neighbor.
the-
Yeah, we can do that. You get extremely good agreement with
get
that.
very
Yeah,
good-
yeah,
you
you
get very good
get
agreement.
fantastic agreement. But this is probing much more than that. The fact that you have
It's
this.
not just local.
Yeah.
this is more.
So roughly, you're looking at
Now, these-
you're looking at
Intermediate time scales.
you're looking at spacings that are like 1 over t
Yeah.
at time t here.
Okay.
So the fact that we get agreement with this linear behavior for a wide range of times is indicating that the pair correlation function is approximately like in random matrix theory for large distances in the bulk of the spectrum. So that's it's a stronger statement than just the short distance universality. Okay, I can tell you the thing. I can tell you one other thing, which I hope will be a way that we can actually compute this curve, and it's also interesting because it has some connections to some other aspects of mathematical physics, which is that there's a limit of this SYK model where you take the parameter q to be very large, and you take the parameter n to be very large, with the quantity q squared over n fixed. So this is the double scale, what we call the double scaling limit. And the theory simplifies somewhat in this limit.
It's a
And
little bit like the spin glass, where you have more.
yeah, that's right. This had been discussed in the context of a spin glass Hamiltonian. Yeah, I'm not sure if they considered.
But it's not the whole hierarchy of replica symmetry grading, which you get in the usual nearest neighbor spin glass or the nearest mean field spin SK model. Here, there's only one symmetry grading.
That means it's one step.
Yeah, one step.
One step Parisi matrices or whatever. Okay. Yeah, but this simplifies the model somewhat. And, well, I'm not sure how much detail. I'm not going to go into much detail here unless there are questions. But one can compute in this model. Well, you can translate the computation of this ZZ star quantity into some combinatorics question that I think can be answered using some methods that I'm just learning about, using these Q Hermite polynomials. Roughly, you're summing over perfect matchings weighted by some parameter to the power of the number of crossings of this perfect matching. And these are the types of expressions that can be summed using.
That is, I think there'd be people who would be actually quite interested.
Yeah, I can illustrate the case that. Yeah. So let me say. Yeah, this is. Well, should I illustrate how one gets that starting from this limit of the model, or illustrate what the problem is that one is dealing with?
What do I see?
The problem or the. Okay. So the problem would be the following. So we would want to study a set of perfect matchings where, let's imagine that we have a collection of variables here. Let's say we have M1 of these guys, and we have some other number, M2 of these guys. And we would like to consider a perfect matching of these. So we can connect like this. and we can also connect like this, and we can connect like that, and so on. So this type of thing.
Can you do longer range stuff on the lines?
Yeah, we could have like that.
The lines can cross.
Yeah, the lines can cross. So we would be studying the sum over these types of perfect matchings, and now we would define the we would want to consider the crossing number of this collection. So the crossing number is the number of lines that we have to pass through each other, so that we get things. Maybe you guys should explain what the crossing number is. Yeah. So the crossing number is
Firstly, you're realizing it in a plane.
Sorry?
It's all to do with a planar realization.
Yeah. Well,
Well,
I think that to explain the crossing number, it's useful to think about planar graphs. Yeah, where we would think about these things as planar.
Those diagrams are not necessarily planar.
These are not necessarily planar, but we can represent them as double line graphs on on planar double line graphs. But we could define the crossing without saying that. It's just the number of times that we need to, for example, move this. So we think about moving this point past that point, and then we have something like that. And each time we have to move a point past another point, we get a factor of e to the minus 2 q squared over n. And this doesn't require any factors, and graphs like this also don't require any factors. So the crossing number is the number of times the number of lines that are crossing here. And these lines are also crossing. So we would compute the crossing number of the graph, we would weight it by this factor, and then we would sum over all possible perfect matchings. And so this is the type of thing that can be, I believe this is the type of thing that can be analyzed using these Q-Hermite polynomials. This is something I'm unfamiliar with, but I've been learning. And one case, yeah.
Analyze, do you mean get an exact value for that?
Yeah, get an exact value for the sum over these matchings.
It's related to the form of this weight.
Yeah, that's right. So maybe I should call it this Q variable. This is the Q in the Q-Hermite polynomial. Will be related to this expression in terms of the model. So one case where we have been able to analyze this, where actually there was a nice paper which was how we learned about this method for the spin glass Hamiltonians. And there, if one is this is the computation for z and z star for this two partition function quantity, where these vertices are associated to z and these ones are associated to z star. There's a simpler problem where you just have z, and then you just consider these types of just one copy and these types of graphs and the sums of these perfect matchings. And there it's easier, and one can indeed write an exact expression for the sum of these things that gives the right answer. I mean, we can check that it's the right answer by comparison to the large N methods. So we would like, in this model, it would be very nice to be able to evaluate this type of sum. And hopefully in this double scaling limit, compute this exact curve.
it's the same curve?
Well, you mean in the double scale limit? Yeah, it's different. So good. It's different in the sense that we've taken n to infinity. So actually, the curve, we'll have to back off the limit slightly to say that we're including some things that are 2 to the minus n. But so that can actually be understood already from the fact that these graphs are proportional to 2 to the minus n. So the fact that we're just including these graphs is slightly illegal in the double scaling limit, but we know that we have to include something that's 2 to the minus n, and this is the leading thing, and we sum these graphs. So I believe that, I think that procedure makes sense. So we would expect the part of the curve that's of order 2 to the minus n to look the same. We would expect to have a ramp and a plateau in that theory.
So this is a way of computing ZZ star. I mean,
hopefully so, yeah. It's at least a way of computing z. And the matching problem is harder for ZZ star, but hopefully we can also compute that. OK, this is the end of the sort of prepared comments. So thank you very much.
It was a formula that Kitaev said.
Formula, yes.
Formula which had a cinch, but he used and had SL2R in it. And he said you had just proved something, and he was trying to give a different proof.
Okay, yeah, that's the formula. That was the formula for the
one over
the Dustermatt-Heckman thing.
Diff
Yeah,
S1,
that's right.
that reduction to the integral over diff S1 was explicitly.
Yeah.
He wanted to do it a different way.
He wanted, yeah, so
He said something about Poincaré measure.
that's right. He was thinking about, yeah, this is actually, it's funny. So naively, this problem with the Schwarzian derivative is, so we're integrating over diff S1 mod SL2R, and then we have this action. The Schwarzian derivative of the element with respect to time. So this is the functional integral one wants to compute. And he was thinking about this as a quantum mechanics problem and trying to understand the Hilbert space. And the Hilbert space is, well, the phase space here is non-compact, but that's sort of because of the SL2R. And he was trying to think about a way of regularizing that SL2R by using the Poincaré measure. And I'm not sure if he's succeeded in that by now. Maybe so. But this,
No,
yeah.
He came to ask me, and then I said, I'll wait till your lecture. And then he said, you would explain what the problem is.
Okay, yeah.
So the problem is what? To make sense of this measure, or to
Maybe to give another derivation.
So he would like another derivation where you think about this path integral.
Representation theory of SL2R.
Yeah, where you think about the path. He wants to think about the Hilbert space. So here we have a path integral we're computing. He wants to think about this. He wants to think about this as a trace of e to the minus beta h.
This is derived using coherent states, I suppose, is it?
No, which is derived?
The path integral.
Evaluated or derived from the
it's
model?
derived.
Derived from the model, it's a long procedure, but no, it involves this disorder average, the large n approximation of this partition function, and then going to low temperature. That's a deriving this action from the fermions is a long story.
Yeah.
So it was evaluating this integral in closed form that we're talking about, that you have done.
Yeah. So this.
And your method.
So there were two methods actually. The first method, where I thought that this would be a complicated function of this parameter here, because in particular when this parameter is small, it doesn't suppress large fluctuations in this field, and you would think that you have to sum over large fluctuations, and that this would be a complicated theory. Now we had computed this by studying these perfect matchings. And the double scaled, you can argue that this theory is part of the double scaled limit. You can take a further limit of that, the triple scaled limit, which just isolates for you this partition function, and you get out of that, you get this sinh of square root of e. So that's one method, but that's sort of weird. I was very surprised by this because Then the third method is that you can just use the Dustermatt-Heckman theorem, which was basically, it was designed to be used for this problem. And it tells you that actually this integral is what's called one loop exact in this variable, where the saddle point approximation plus the determinant about the saddle point is the exact answer. And so these give the same answer. So here, from this way, you find it's 1 over beta j to the 3/2 e to the n over beta j, and from the double scaled limit, you directly compute this rho of e, and then I promise that if you compute dE, rho of e to the minus beta e, with that rho, you get this answer. So, and I think that Kitaev is trying to find a third method where he thinks about this in terms of a Hilbert space and directly computes this. Yeah, you would like to think about this rho of e as a regularized measure on this Hilbert space. I haven't understood exactly how he's thinking about this, but that's the rough idea.
Of course, I suppose this expression that you've got written there is not exact in terms. I mean, the answer is exact, but it's not the connection with the quantum model.
That's right.
Exact.
That's right. That's absolutely right.
All kinds of approximations being made to get it.
Yeah, low temperature, and so I think I think it's exact for, it should be exact for low temperature. So this means that beta j is much bigger than 1. But it should be much smaller than like e to the alpha n for any value, for some value of alpha. So I think there will be large corrections to this analysis when beta j gets so small. That would be at least one source of corrections. There could be larger corrections.
So part of it is trying to understand what these other corrections are. So if you had a Hilbert space, perhaps perspective, you could get.
Oh yeah, but no, he's just trying to study this theory. He's trying to.
It's just this one.
He's trying to. He's trying to do this.
He's also trying to
I
relate.
think he's also trying to relate it to the Plancherel measure of SL2R,
Yes.
which is.
Is it close to that?
Yeah, very close.
It is.
And so you could, maybe there's some way of taking his model. The representations of SL2R which are unitary, or infinite dimensional. They're
Yes.
identified
Right,
by
right.
quantum.
And then there's a weight.
And there's a weight there in what's called the Plancherel formula,
Yeah.
and that was computed by Bogman probably, or somebody like that. And but the question, maybe he's trying, has nobody tried to put this, the very first thing you put down is Majorana
Yeah.
algebra.
Yeah.
Maybe there, I'm sure that that's been put, I need to look at what Kirillov did. I think he studied a lot the representation theory at diff S1.
Okay. Diff S1 or diff S1 and mod SL2R.
I think that probably is built into anything.
Okay.
That's kind of a natural thing. The Schwarzschild
Okay.
is the only invariant.
Yeah.
So okay, there was a cryptic comment which was told to me by a mathematical physicist, which I didn't understand, which I think would be helpful if I understood, which was that the Schwarzschild is that there are a family of commuting functions, symplectically commuting functions on the space diff S1 mod SL2R that includes the Schwarzschild, and then a family of other things that are built out of Schwarzschiilds. Okay, is that okay?
You'll have to go look at Kirillov's work.
Okay.
Or him and many people who were working on. So when people were working on integrals of a mass is one dimension smaller. This is the boundary of the hyperbolic plane. And so diff S1 acts there, and a functional integral like that should be much easier to work with.
Okay.
This looks like a doable, almost doable mathematical problem. Anyway, one understands the representation theory of SL2R. Then people are trying to understand representations of theory of something like diff S1.
Okay.
That's about the only infinite dimensional group I think that there's any kind of mathematical theory. And a lot of it involves extending functions from the boundary to the disk and looking at the actions there. There's some regularization.
So you've got some Virasoro algebra acting.
Yeah, probably.
Yeah. Well, I'm not sure. You can use. Yeah, you can think of diff S1 mod SL2R as a coadjoint orbit of the Virasoro group.
Yeah. So he
I'm
invented
not sure.
coadjoint orbits.
Okay.
So
Okay, so he's the person who would.
He's the
Okay.
inventor of the thing.
Okay. Okay. Yeah, this stuff is all very new to me. Actually, this is not my my. I was surprised. Frankly, I was shocked by the fact that this simple theory without any supersymmetry ended up sort of coming into contact with sophisticated mathematics, and this is I think probably there's more contact than has yet been uncovered, but it was a real surprise for me.
The natural invariance properties, maybe this integral can be almost evaluated by just invariance properties up to a scalar or something. Like you write this functional integral down and say, well, is the SL2R the only natural invariance?
There's also a U1.
Okay.
But that's, as far as I know, that's it. Maybe there's something more lurking, but
You mean so you can see this directly in the model, in the quantum model or not?
you can see what directly?
The SL2R or SL.
Yeah. You can see that SL2R, starting from the original model, is a gauge symmetry of the problem. Yeah. So.
Yeah. So no wonder it's natural to think about the representation. Well, Douglas, thank you very much for a wonderful exposition.
Yeah, thank you. This was
Appreciate it
fun.
very much.